Okay, so we're moving on here with part two, and we're going to find the area under the graph of a function. So in this next example, instead of using a specific number of approximate of rectangles to approximate the area, we're going to use a general number of subintervals called n, and let n approach infinity, and we're going to actually get the true area under the curve. So in this case, we're not actually going to use a curve. We're going to use a line. So find the area under the graph of f of x equals 3x from 0 to 10 using upper sums, and that is find the area at that is the limit as n approaches infinity. So if I actually draw this, so we have the graph of f of x equals 3x here. If I go from 0 to 10, then I want the area of this region right here. So notice that this point right here is at 10 comma 30. It's a triangle. I could actually use geometry. So 1/2 the base times the height. So it's 5 times 30, so you get 150. Okay. But I want to actually use calculus to determine the area under the graph here. So I'm going to use delta x, which is b minus a 10 minus 0 over n. And remember, I'm going to just use a general number of rectangles, so this formula only simplifies to 10 over n. Okay, so I'm going to let I equal the rectangle that I'm on. So if I equals 1, 2, 3, 4, 5, 6, I'm on the first, second, third, fourth, fifth, sixth, and so forth rectangles. Okay, so the endpoints of each subinterval written in terms of n are going to be x. So like x of 0 would be 0. That's the first rectangle. X of 1 is going to be 10 over n. X of 2 is going to be 2 times 10 over n. X of 3 is going to be 3 times 10 over n, because to get to that endpoint, you have to use delta x um, 3 times essentially. So if I want to go to the fifth rectangle, I would have to do delta x 5 times, so 10 over n times 5, and so forth and so on. In general, the ith x value or ith rectangle is going to be 10 over n times I. Okay? So keep track of all that because it's going to all come together in a second here. So the sum, Sn, or the area, is equal to the sum, of I equals 1 to n of f of ci delta x. In this case, that would be uh, sum I equals 1 to n of, if I plug xi, I put c, but we're going to do xi, into this function, then I would have 3xi times delta x, which we said was 10 over n. Now, xi, we said was 10 over n times I. So this would be 3 times 10 over n times I times delta x, which was 10 over n. I equals 1 to n. Okay. Now we could simplify this a bit, and we have sum I equals 1 to n of 300 over n squared I. Now this is just the formula, and we do have some formulas for the terms of a sequence. If you have the sum of just a constant, it's just that constant that many times. If you have the sum of k, so if this k goes from 1 to n, then you'd have like 1 plus 2 plus 3 plus 4. The formula is just whatever n is times n plus 1 over 2. If you have the sum of squareds, then this is the formula. If you have the sum of cubes, then this is the formula. Okay, so using the properties of summation, in here the index of summation is I, n is the number of rectangles. So we can think of n as being a constant. So we could factor out the 300 over n squared times the sum formula for I, which is going to be the same as this sum formula here. They just use K for the formulas, but we used I for the index of summation here. So 300 over n squared times the sum formula for the sum of I, or the sum of K, which is going to be n times n plus 1 over 2. Now we can do some canceling here because the n and the n squared can cancel, the 300 and the 2 can cancel to 150. All right. Since I use the sum formula, this summation notation is no longer necessary. So I would have 150 times n plus 1 over n. If I break that apart and distribute, that's going to be 150 times n over n plus 1 over n. Okay, I'm kind of running out of some room here. Now, this simplifies to 150 times 1 plus 1 over n. Now, if I take the limit of that as n approaches infinity, then of 150 times 1 plus 1 over n, the 1 over n is going to go to 0 as n approaches infinity, and my answer is 150. Now, that's a lot of work to kind of prove that the area of this triangle essentially is 150 that we use by geometric formulas. But we did that in order to illustrate how to solve this type of problem. So let's go ahead and do another one where we find the area using lower sums. So let me erase some of this stuff right here so that we have some room to work. Okay. Now I want to find the area under the graph of f of x equals 16 minus x squared from 0 to 4 by using lower sums, rectangles that lie below the graph of f. So I do have the whole graph here, but notice we're going to go from 0 to 4. If I just pick a random subinterval, go from like here to here, and draw vertical lines, I want to use lower sums in other words, sums that are going to under approximate. So to do that on this portion of the graph, since it's decreasing, I would have to use the upper value of each subinterval. Okay, so I know that my delta x is going to be 4 minus 0 over n, or 4 over n. Okay, the first x value, so like x0, is going to be 0. Then x1 is 1 times 4 over n. Then x2 is going to be 2 times 4 over n. And then the ith x value is going to be I times 4 over n. So xi is equal to 4 over n times I. So all that is telling me is that is the x value in general that I'm going to use to evaluate the function to get its height at the right endpoint of each subinterval. So I would evaluate the function at xi. So 16 minus 4i over n squared. Okay, so this is going to be 16 minus 16i squared over n squared. All right. And then the next step we want to do is set up the summation formula to get the area. So the sum is equal to summation notation I equals 1 to n of f of xi delta x. It's always going to be the same because the f of xi is the height of the ith rectangle, delta x is the width. Since all the subintervals are the same width, we can use the width here that we got, which was 4 over n. So we can rewrite this sum I equals 1 to n of f of xi, which is 16 minus 16i squared over n squared, times delta x, which was 4 over n. Okay? Now, if I simplify and distribute here, I would have sum I equals 1 to n of 64 over n minus 64i squared over n squared. Okay, which I can break this apart. So since you have addition and subtraction here, and we can treat the 64 over n and 64 over n squared. Oops, I forgot. This is squared, so this one would be cubed. So we can break it apart and have 64 over n, I equals 1 to n, of 1 minus 64 over n cubed, sum I equals 1 to n of I squared. And then what we're going to do is we're going to use these summation properties. Notice we have 1 here, so that's the first property. And then we have I squared here, which is the third property for k squared here. So the summation formula for sum of 1 is just adding 1 repeatedly, so n times. So this is going to be 64 over n times n. This is going to be minus 64 over n cubed times the sum formula for I squared, which is n times n plus 1 times 2n plus 1 over 6. So n times n plus 1 times 2n plus 1 all over 6. Okay, so this 64 over n and the n are going to cancel. Here we could cancel a factor of n with this n cubed and make it squared. Okay, so this is going to be 64 minus the 64 here and the 6 can cancel to 32 and 3. So this is going to be 32 over 3n squared times, now if I FOIL the n plus 1 times 2n plus 1, you're going to get 2n squared plus 3n plus 1. Okay. Now, you don't have to go too much farther because we're eventually going to take the limit, but we want to simplify enough so that we can cancel all the n's that we can. So you'd have 64 minus 64 over 3 if I distribute it here, because the n's would cancel. If I distribute it here, it's going to be minus 32 over n, because the 3's will cancel and a factor of n will as well. And when I distribute it there, you'd have minus 32 over 3n squared. Now, if I take the limit as n approaches infinity, this term goes to 0, as does this one, and you have 64 minus 64 thirds, which gives you 128 over 3. So the area under the graph of f of x equals 16 minus x squared from 0 to 4 is 128 square units. Okay, so that's it for this section. Hope that was helpful to you guys, and take care.